Welcome back to the Sleepy Planet Show, where we explore the world one yawn at a time. Tonight, Nate embarking on a slow, soothing journey into one of the most mind-bending ideas in all of science, the theory of a parallel universe. It's a concept that feels like it belongs in comic books and late-night movies, a fantastical realm of doppelgangers and alternate histories. But what if I told you that this idea, in its various forms, emerges not from fiction, but from the deepest, most rigorous equations of physics? What if our universe is not the whole story, but just a single page in an infinite cosmic library? As always, I hope this gentle exploration helps you drift off into a peaceful sleep, or at least helps you feel a little more connected to the vast, strange wonder of existence. Of course, there's a small chance that contemplating infinite versions of yourself might be too interesting and keep you awake. But if that happens, well, at least you'll have some truly fascinating possibilities to dream about. Before we slip into the cosmic currents together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow. I'd also love to know where you're watching from and what time it is for you right now. Are you listening from a quiet study in Kyoto at 1 a.m. or tuning in from a hammock in Costa Rica on a sunny afternoon? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe. Now, settle in, get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like a gentle stream, branching into endless possibilities. And as we begin this quiet voyage into the great cosmic maybe, remember, this video is for educational and relaxation purposes only and is not intended as medical advice or a substitute for professional treatment. Ready? Let's begin. What is a universe? Defining our home ground. Before we can set sail on the cosmic ocean in search of other shores, it helps to have a good map of our own island. What exactly is our universe? What are its rules, its ingredients, its fundamental character? When we say the word universe, we're talking about everything we can, in principle, ever see, touch, or interact with. It's the sum total of all space, time, matter, and energy as we know it. A single, vast, interconnected system governed by a consistent set of laws. Our universe, as we understand it, has a story. It began about 13.8 billion years ago in a state of unimaginable heat and density, an event we gently call the Big Bang. From that single explosive moment of becoming, space itself began to expand, and it has been expanding ever since, carrying galaxies along with it like flecks of glitter on the surface of an inflating balloon. Within this expanding space, everything is choreographed by just four fundamental forces. There's gravity, the silent, long-reaching force that pulls galaxies together and keeps your feet on the ground. It's the gentle curve in space-time that dictates motion on the grandest scales. Then there's electromagnetism, the force that governs light, electricity, and magnetism. It's the reason magnets stick to your fridge, the reason the sun warms your face, and the force that binds atoms together into molecules. Down at the subatomic level, two other forces rule the roost. The strong nuclear force is the cosmic superglue, binding protons and neutrons together in the heart of an atom. It's incredibly powerful, but works only over minuscule distances. Finally, there's the weak nuclear force, a more subtle player, responsible for radioactive decay, the process that allows a neutron to change into a proton, helping to power the stars. These four forces dictate all the interactions in our universe. And what are the actors in this cosmic play? All the matter we see, from the largest star to the smallest grain of sand, is made from a surprisingly small menu of elementary particles. This is often called the standard model of particle physics. There are quarks, which huddle together to form protons and neutrons. And there are leptons, the most famous of which is the electron, the tiny particle that orbits atomic nuclei and carries electric charge. These particles interact by exchanging other particles called bosons. The photon, for instance, is the boson that carries the electromagnetic force. Think of it as a tiny messenger carrying a note from one particle to another. All of these rules, forces, and particles are governed by a set of numbers called fundamental constants. These are the deep settings of our universe. The most famous is the speed of light, c, the ultimate cosmic speed limit that nothing with mass can exceed. There's also the gravitational constant, g, which sets the strength of gravity, and Planck's constant, h, which governs the strange, fuzzy rules of the quantum world. These numbers seem to be precisely tuned for a universe like ours to exist. If you were to change the strength of the strong nuclear force by just a tiny fraction, stars couldn't form. If you tweaked the mass of the electron, chemistry as we know it would be impossible. Our universe is a delicate balance, a finely tuned machine that allows for complexity, structure, and, on at least one small blue planet, life. This is our home ground. This specific combination of a Big Bang origin, four forces, a dozen or so elementary particles, and a handful of finely tuned constants. This is what we mean when we say our universe. It is the baseline reality, the familiar shore from which we are about to gaze out at the possibility of other, stranger oceans. Before we can ask if there are other universes, we must first appreciate the unique and specific nature of our own. It is our control group in the grandest experiment of all. So take a slow, deep breath. Feel the gentle pull of gravity, the warmth of electromagnetic radiation from a nearby lamp, the solid matter beneath you held together by the strong force. You are a citizen of this universe, built from its stardust and governed by its laws. And now, with our feet firmly planted on this home soil, we can quietly begin to wonder, is this all there is? The first whisper, quantum strangeness. Our journey into the multiverse doesn't begin by looking through a telescope at the farthest reaches of space. It starts by looking inward at the smallest, most fundamental level of reality. It begins in the strange, ghostly realm of quantum mechanics. For most of human history, we thought the world was predictable. If you roll a ball, you can calculate its path. If you know where something is and how fast it's moving, you can predict where it will be. The universe was seen as a giant, intricate clockwork mechanism, ticking along according to deterministic laws. Then, in the early 20th century, physicists peering into the world of the atom found something deeply unsettling. The clockwork was gone. In its place was a world of fog, probability, and pure weirdness. One of the central ideas of this quantum world is superposition. At its heart, superposition means that a particle, like an electron, doesn't have a definite property until you measure it. Before you look, it's not in one specific place. It exists in a cloud of possibilities. It can be here, there, and everywhere all at once, described by something called a wave function. Imagine a spinning coin. While it's in the air, spinning, it's not heads or tails. It's in a combination of both states. Only when it lands and you look at it does it choose one outcome. A quantum particle is a bit like that spinning coin, but it can be in a superposition of many more properties: position, spin, momentum, all at once. This idea was famously and gently illustrated by the physicist Erwin Schrödinger with his thought experiment involving a cat. Imagine a cat placed in a sealed box. Inside the box is a vial of poison connected to a radioactive atom. If the atom decays, a purely random quantum event, the vial shatters and the cat, sadly, dies. If the atom doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe the system, the atom is in a superposition of both decayed and not decayed. And if the atom is in a superposition, then so is the cat. The cat is both alive and dead at the same time, existing in a ghostly blend of both realities.
This isn't just a philosophical quirk. It's backed by countless experiments. Another bizarre quantum rule is the Heisenberg uncertainty principle. It states that there's a fundamental limit to how well you can know certain pairs of properties of a particle. For example, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. It's not a limitation of our instruments, it's a fundamental property of nature. The universe has a built-in fuzziness, a gentle blur that can never be brought into perfect focus. Particles are not tiny billiard balls, they are waves of probability. This is called wave-particle duality. Sometimes an electron acts like a solid little particle, and other times it acts like a spread-out wave. It depends on how you measure it. All of this strangeness leads to a profound question known as the measurement problem. What happens when we actually look at a quantum system? When we open Schrödinger's box, we don't see a ghost cat that is both alive and dead. We see one or the other. The cloud of possibilities seems to collapse into a single, definite reality. But why and how? What is so special about the act of measurement that it forces the universe to make a choice? For decades, physicists were content with the idea that the wave function just collapses. It was a mathematical trick that worked, even if no one knew what it meant. The spinning coin lands, and that's that. But this answer felt incomplete, like stopping a story right at the climax. It seemed to give human observation a strange, almost magical power over the fundamental workings of reality. This deep dissatisfaction with the idea of collapse is what opened the first door to the multiverse. A young physicist in the 1950s looked at this problem and proposed a radical, elegant, and breathtaking alternative. What if, he wondered, the universe never chooses at all? What if the coin doesn't just land on one side? What if, in the quiet moment of measurement, reality itself splits in two, and both outcomes happen? This was the first whisper of the multiverse, born not from cosmology, but from the deep and unsettling mystery at the very heart of matter. Branching realities. The many worlds interpretation. Imagine you're standing at a fork in a quiet wooded path. You can go left or you can go right. You pause, weigh your options, and eventually choose the path to the left. In our everyday understanding of the world, that's the end of the story. The path to the right becomes the road not taken, a fading possibility that exists only in your memory. But what if that's not what happens? What if in the moment of your decision, the entire universe splits in two? In one universe, you take the left path. But in another, perfectly real universe, a copy of you takes the path to the right. Both choices are realized. Both paths are walked. This is the staggering, beautiful, and deeply strange idea at the heart of the many worlds interpretation of quantum mechanics. Proposed in 1957 by a brilliant but unconventional physicist named Hugh Everett III, this interpretation offers a radical solution to the measurement problem we just discussed. Everett looked at the collapse of the wave function, the idea that a particle in a superposition of many states suddenly picks one when measured, and found it unsatisfactory. It was an extra rule tacked on to quantum theory that seemed arbitrary and clumsy. He proposed a simpler, more elegant idea. The collapse never happens. Instead of the universe choosing one outcome from a field of possibilities, all possible outcomes happen. Every time a quantum event occurs that has more than one potential result, the universe itself branches. A new timeline is created for each and every possibility. The wave function never collapses, it just evolves, describing the entirety of this branching, ever-growing tree of realities. Let's go back to Schrödinger's cat. In the traditional view, when you open the box, the superposition collapses, and you find either a living cat or a dead cat. In the many worlds view, when you open the box, the universe splits. In one branch, you open the box and find a living cat. You are relieved. You give the cat a gentle scratch behind the ears, and you continue on with your day in that universe. In the other branch, a copy of you opens an identical box and finds, tragically, a dead cat. You are saddened and continue on with your day in that universe. Both outcomes are equally real. Both versions of you are equally you. They just can't communicate with each other. Once the split occurs, the two universes are completely separate, evolving on their own parallel tracks, unaware of the other's existence. This applies to every quantum event. The decay of a single radioactive atom, a photon hitting a detector, an electron choosing a path. Every tiny, probabilistic flicker at the heart of reality causes a new split in the universal timeline. The result is not a single universe, but a vast, ever-branching collection of parallel universes, a quantum multiverse. The number of these universes is unimaginably large, growing exponentially with every passing fraction of a second. This idea can feel overwhelming, even a little unsettling. The thought of infinite versions of yourself living out the consequences of every choice you ever made and every choice you didn't is a lot to take in. There's a universe where you took that job you turned down. There's a universe where you said what you wished you'd said. A universe where you had a different breakfast this morning. And for every one of those universes, there are countless others that are almost identical, differing only in the position of a single stray atom. However, Everett and proponents of this view see it not as a complication, but as a simplification. It removes the need for the mysterious collapse and just lets the equations of quantum mechanics do their thing. The universe simply follows the rules, and the branching is a natural consequence. There's no need for a special role for observers or consciousness. The splitting happens whether a human is there to see it or not. You don't create the branches with your choices, you are simply carried along one of the streams. Think of reality as a great river. As it flows, it constantly encounters obstacles and splits, forming new channels and tributaries. You're in a boat on this river. You only experience one path, one stream, but the river itself contains all the paths. You can't see the other streams, but they are just as much a part of the river as yours. One of the deepest questions this raises is about identity. If there's another you who chose differently, are they still you? From a physics perspective, yes. Before the split, you were one and the same person. After the split, you are two separate people with a shared past. You can't feel their feelings or know their thoughts, just as you can't feel the thoughts of your own past self. You are defined by the branch of reality you inhabit. While we can't test this idea directly, we can't peek into the other branches or send them a message, it remains one of the leading interpretations of quantum mechanics among many physicists. It is taken seriously not because it's sensational, but because it is mathematically clean and logically consistent. It takes the strangeness of quantum mechanics at face value and follows it to its logical conclusion, no matter how profoundly it alters our view of reality. It suggests that the universe is far, far larger and more wonderful than we ever imagined. Not just one story, but an infinite collection of tales, all being written at once. Cosmic bubbles, the inflationary multiverse. Now, let's zoom out. Let's leave the strange, fuzzy world of the atom and travel to the very beginning of time and space. Here, on the vast canvas of cosmology, we find another completely independent reason to believe in a multiverse. This idea doesn't come from quantum branching, but from the explosive birth of our own universe. For a long time, the standard Big Bang theory had a few nagging puzzles. For one, the universe looks remarkably uniform on the largest scales. The temperature of the cosmic microwave background, the faint afterglow of the Big Bang, is almost exactly the same in every direction we look. This is strange, because regions of the sky that are on opposite horizons from our point of view were never close enough to each other to have mixed and evened out their temperatures. It's like finding that two people on opposite sides of the earth who have never met or communicated have somehow chosen to wear the exact same outfit. It demands an explanation. In the 1980s, a theory called cosmic inflation was proposed to solve this and other puzzles. The idea is that in the first fraction of a second after the Big Bang, the universe underwent a period of mind-bogglingly rapid, exponential expansion. It grew from something smaller than a proton to something larger than a grapefruit in less than a trillionth of a second, expanding far, far faster than the speed of light. This isn't a violation of relativity, because it was space itself that was expanding, not objects moving through space. This hyper-expansion would have taken a tiny, smooth, connected patch of the early universe and stretched it out to become the enormous, flat, and uniform universe we see today. The two people on opposite sides of the Earth now make sense. They were once neighbors, infinitesimally close before inflation stretched the fabric of space between them. Inflation is now a cornerstone of modern cosmology, supported by detailed observations of the cosmic microwave background. But some of its architects soon realized that it had a startling consequence. According to the theory, inflation might not have been a one-time event. It could be eternal. This idea is called eternal inflation. Imagine the universe as a whole is a vast, eternally inflating ocean of energy. Within this ocean, inflation is the default state. It's always happening. However, in some places, like a pot of boiling water, bubbles can form. In these bubbles, the inflationary energy converts into matter and radiation, and inflation stops. A hot Big Bang occurs, and a new universe is born. Each of these bubbles becomes a self-contained universe, expanding and evolving on its own, like ours. In this picture, our universe is just one bubble in an endless, frothing cosmic foam. The inflating ocean of energy, sometimes called the bulk, is constantly spawning new bubble universes. Our Big Bang wasn't the beginning of everything, but just the moment our particular bubble nucleated and began to expand. This is the inflationary multiverse, sometimes called the bubble universe model. Think of it like a cosmic soda. The soda itself is the inflating space, and the little bubbles of fizz that appear are individual universes. They are causally disconnected from each other. The space between the bubbles is expanding so rapidly that even if you could travel at the speed of light, you could never cross the gulf from one bubble to another. We are forever isolated within our own cosmic bubble. What makes this idea even more fascinating is that each bubble could be different. The way the inflationary energy converts into matter and energy might be different in each case. This means that other bubble universes could have completely different laws of physics. Some might have stronger gravity. Some might have different elementary particles. Some might even have a different number of spatial dimensions. Most of these universes would likely be sterile and inhospitable. They might collapse back on themselves in an instant, or expand so quickly that no stars or galaxies could ever form. They would be cosmic stillbirths, fleeting and empty. But in a foam of an infinite or near infinite number of bubbles, it's not surprising that some, by pure chance, would have just the right conditions for complexity and life to emerge. We, of course, find ourselves living in one of these lucky bubbles. This provides a potential explanation for the fine-tuning problem we mentioned earlier, why the constants of our universe seem so perfectly set for our existence. It's not that they were designed for us, it's that we could only exist in a universe where they happen to have the right values. This is a form of the anthropic principle. We won a cosmic lottery, not because we are special, but because there were an infinite number of tickets. This inflationary multiverse is a very different beast from the quantum multiverse of many worlds. The many worlds universes are all part of the same bubble, branching off from each other at every quantum event. They share the same fundamental laws of physics. The bubble universes are physically separate realms, born from a larger substrate,
each potentially with its own unique physics. One is a branching tree. The other is a sea of separate islands. Both ideas are breathtaking in their scope. They both suggest that what we call the universe is only a small part of a much grander, more complex reality. And while we may never be able to visit these other bubbles, their potential existence reframes our place in the cosmos. We are not the center of the universe. Our galaxy is not the center. And perhaps our entire universe is not the center either, but just one quiet, gentle bubble in a sea of infinite possibility. A landscape of possibilities, string theory, and brains. Our journey into the multiverse now takes us to the very frontier of theoretical physics, into a realm of beautiful mathematics, extra dimensions, and tiny vibrating strings. This is the world of string theory, one of the most ambitious and controversial ideas in science. For decades, physicists have dreamed of a single elegant theory that could unite the two great pillars of modern physics: Einstein's general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which describes the other forces and the subatomic world. A theory of everything. String theory is perhaps our best, though still incomplete candidate for such a theory. The central idea of string theory is deceptively simple. It proposes that the fundamental constituents of reality are not point-like particles, but tiny one-dimensional vibrating filaments of energy called strings. Each string is imaginably small, far smaller than a proton. Just like a violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings can vibrate in different patterns. According to the theory, each unique vibrational pattern corresponds to a different kind of particle. One pattern of vibration makes a string appear to us as an electron. Another pattern makes it a photon, another a quark. And one specific vibration, the theory predicts, corresponds to the graviton, the hypothetical particle that carries the force of gravity. In this view, the entire rich zoo of particles we see in our universe is nothing but the different notes of a single underlying cosmic symphony, played on these tiny strings. It's a beautiful and powerful idea. But it comes with a strange requirement. For the mathematics of string theory to work, the universe must have more dimensions than the three of space, length, width, and height, and one of time that we experience. Depending on the version of the theory, it requires a total of 10, 11, or even 26 dimensions. So where are these extra dimensions? The prevailing idea is that they are compactified, curled up on themselves at an incredibly small scale, the so-called Planck length. Imagine a garden hose. From far away, it looks like a one-dimensional line. But if you get very close, you see it has a second dimension, the circumference you could walk around. The extra dimensions of string theory are thought to be like that circumference, curled up so tightly at every point in space that we are completely unaware of their existence.
This is where another door to the multiverse opens. The shape of these curled up extra dimensions is not fixed. iterations of string theory allow for a staggering number of possible ways for these dimensions to be folded and shaped. These shapes are known as Calabi-Yau manifolds. The number of possible shapes is truly immense, estimated to be at least 10 to the power of 500. That's a 1 followed by 500 zeros. Each of these different shapes for the extra dimensions would result in a different set of physical laws in the large, three-dimensional world we experience. The way the strings can vibrate depends on the geometry of the space they are vibrating in. A different shape means a different set of possible notes, and therefore a different set of particles and forces. This vast number of possible solutions is called the string theory landscape. Now, if you combine this idea with the eternal inflation model we just discussed, you get a powerful picture of a multiverse. As new bubble universes are born in the eternally inflating sea, each one could land on a different point in the string theory landscape. Each bubble would have its extra dimensions curled up in a different way, leading to a unique set of physical laws. One bubble might have the physics of our universe. Another might have no gravity. A third might have 10 different kinds of electrons. The landscape provides the menu of possibilities, and eternal inflation provides the mechanism for realizing them. This synthesis suggests that not only do other universes exist, but there is a near infinite variety of them, each corresponding to a different mathematical solution to the theory of everything. But string theory offers yet another, even more direct vision of a multiverse. In a more advanced version of the theory, called M-theory, which lives in 11 dimensions, reality is not just made of strings, but also of higher dimensional objects called membranes, or brains for short. A brain can have any number of dimensions. A 0 brain is a point, a 1 brain is a string, a 2 brain is a plane, and so on. In this picture, our entire three-dimensional universe could be a giant brain floating within a higher dimensional space, the bulk. We and all the particles and forces of the standard model, except gravity, are stuck to this brain. We can't move off it, just as a character drawn on a sheet of paper can't jump off the page. We're confined to our 3 brain. This leads to the brain multiverse model. There could be other brains, other universes, floating parallel to ours in the higher dimensional bulk. They might just be a millimeter away from us, but in a direction we can't perceive. Imagine a loaf of sliced bread. Each slice is a universe, and the space between the slices is the bulk. We live on one slice and cannot access the others. This model has some tantalizing, though speculative, possibilities. While we are stuck on our brain, gravity, being the geometry of space-time itself, might not be. Gravity could leak between the brains through the bulk. This could explain why gravity seems so much weaker than the other forces. Most of its strength is diluted by spreading out into the extra dimensions. This vision of parallel worlds separated by a tiny gap in a hidden dimension is perhaps the most iconic image of the multiverse, a quiet, elegant collection of realities stacked just out of sight. Echoes from another world, searching for evidence. We have now journeyed through several strange and beautiful conceptions of the multiverse. The endlessly branching timelines of many worlds, the frothing sea of bubble universes from eternal inflation, and the parallel sheets of reality predicted by string theory. At this point, it is perfectly natural to feel a sense of gentle skepticism. These ideas are magnificent, but are they science? Or are they just a form of metaphysical speculation, a kind of modern mythology written in the language of mathematics? The heart of the scientific method is testability. A good scientific theory must make predictions that can, at least in principle, be checked against observation. If a theory cannot be tested or proven wrong, it risks falling outside the realm of science. So, the elephant in the room is a very large one. Is there any way to find evidence for these other universes? The challenge is immense. By their very nature, most of these parallel worlds are causally disconnected from our own. We can't send a probe to a neighboring bubble universe, nor can we peek into the quantum branch where we chose a different path. The barriers seem absolute. However, that hasn't stopped some of the world's most creative physicists from thinking about potential indirect ways to see a faint echo from another world. These are long shots, whispers on the edge of detectability, but they are not impossible. Let's start with the inflationary multiverse, the idea of our universe as one bubble among many. If other bubbles formed near ours in the early moments of creation, they might have collided before the rapidly expanding space between them pushed them forever apart. Such a cosmic bump, a collision between universes, would have been an event of cataclysmic energy. It would have left a lasting imprint, a kind of cosmic bruise on our own universe. Where would we look for such a bruise? The best place is the cosmic microwave background, the faint afterglow of our own Big Bang. The CMB is a baby picture of our universe, and it is incredibly uniform, but not perfectly so. If another universe collided with ours, it could have created a disturbance that would show up today as a specific pattern in the temperature fluctuations of the CMB. Perhaps a distinctive circular spot that is slightly warmer or cooler than its surroundings. Scientists have been meticulously searching the CMB data from satellites like WMAP and Planck for such a telltale signature. Over the years, a few anomalous spots have been identified and debated. Some researchers have claimed they could be evidence of a bubble collision, while others have argued they are more likely to be statistical flukes or effects from more mundane sources within our own galaxy. So far, the evidence is inconclusive and highly controversial. There is no smoking gun, no definitive proof, but it's a tantalizing possibility that a faint circle of light in the oldest picture we have of our cosmos could be an echo from another world. What about the brain multiverse from string theory? If our universe is a three-brain floating in a higher dimensional book, could we detect the presence of other brains? One idea, as we touched on, relates to gravity. In some brain models, gravity is the only force that can travel through the bulk between brains. This could lead to observable consequences. For example, if two brains were to collide, the collision would produce a massive burst of gravitational waves, ripples in the fabric of space-time, that could potentially be detected. Some have even proposed that our own Big Bang was the result of such a brain collision. Another exotic possibility is that particles from our brain could, under very high energy conditions, be knocked off into the bulk. If this were to happen,
in a particle accelerator like the Large Hadron Collider, it would manifest as energy and momentum seemingly disappearing from the experiment, vanishing into the extra dimensions. Again, extensive searches for such effects have so far come empty. Even the many worlds interpretation of quantum mechanics, which seems the most hermetically sealed, has prompted some creative, albeit highly speculative, thinking about tests. Some physicists have argued that the interactions between the branching worlds might not be perfectly zero. There might be a tiny, residual influence from the other versions of a system on our own branch. Detecting such an influence would be extraordinarily difficult, far beyond our current technological capabilities, but it highlights the drive to bring these ideas, no matter how strange, into the realm of empirical science. It's important to maintain a sense of perspective. Right now, there is no direct, verifiable evidence for any kind of multiverse. These potential signals are long shots, needles in a cosmic haystack. For many scientists, this lack of testability is the theory's greatest weakness. They argue that until we can make a concrete, testable prediction, the multiverse remains a philosophical playground rather than a scientific theory. But for others, the fact that these multiverse ideas emerge naturally from our best and most promising theories, quantum mechanics, inflation, and string theory, is evidence in itself. They see the multiverse not as an ad hoc addition, but as an unavoidable consequence of where the logic of physics leads us. The search continues, quietly and patiently. We listen for faint whispers in the cosmic static. We look for subtle anomalies in the patterns of light, and we dream of finding a crack in the wall of our own reality. Even if we never find it, The search itself expands our understanding of what might be possible. The mathematical universe. Is reality just a formula? We have explored multiverses that branch, bubble, and float parallel to one another. These are all, in a sense, variations on a theme. They imagine other universes that are still fundamentally physical, made of space, time, and energy, even if the specific rules are different. But now we arrive at the most abstract, the most mind-expanding, and perhaps the most profound vision of the multiverse. This is the idea that the ultimate reality is not physical at all, but mathematical. Welcome to the Mathematical Universe Hypothesis, or MUH, championed by cosmologist Max Tegmark. This is what he calls the Level 4 multiverse, and it suggests that every mathematically consistent structure corresponds to a physical reality. In other words, if a universe can be described by mathematics, it exists. To understand this, we must first appreciate the deep and mysterious connection between physics and mathematics. As scientists have probed the universe more deeply, they have found time and time again that its workings can be described with stunning accuracy by elegant mathematical equations. From the elliptical orbits of planets to the complex dance of subatomic particles, reality seems to have a mathematical blueprint. Galileo famously said that the universe is a grand book written in the language of mathematics. The mathematical universe hypothesis takes this idea to its ultimate conclusion. It proposes that the universe is not just described by mathematics, it is a mathematical structure. What does that even mean? Think of it this way. A physicist can write down a set of equations that completely describe a hypothetical universe, its particles, its forces, its dimensions. In the traditional view, we would then have to go out and check if our physical universe matches those equations. But in the MUH, the act of mathematical existence is the same as physical existence. Every set of equations that is internally consistent, that doesn't contradict itself, describes a real universe. There is one mathematical structure that corresponds to our universe, with its specific particles and forces. But there are countless others. There would be universes that obey Newton's laws instead of Einstein's, universes with 2 dimensions of time, universes based on entirely different logical systems, universes so bizarre and alien that we can't even begin to imagine them, but which can be described by a consistent mathematical formalism. This is the most all-encompassing version of the multiverse. It doesn't just contain universes with different physical constants, like the bubble multiverse, or different quantum outcomes like the many worlds multiverse. It contains every possible reality that can be imagined by a mathematician. Why would anyone propose such a radical idea? Tegmark argues that it offers the ultimate answer to the question, Why these laws of physics and not others? The answer in the MUH is that there is no answer. All possible laws exist in their own respective universes. We find ourselves in this one for the same anthropic reason as before. It's one of the few that is complex enough to support self-aware beings capable of asking the question in the first place. This hypothesis elegantly removes the need for a creator or a selector of physical laws. Reality is simply the exhaustive expression of all mathematical possibility. The idea also addresses a deep philosophical puzzle called the unreasonable effectiveness of mathematics in describing the natural world. Why should the abstract, logical constructions of the human mind map so perfectly onto the workings of the cosmos? The MUH answers that it's because the cosmos itself is one of those abstract, logical constructions. We are not just discovering the mathematical patterns in reality. We are discovering the very substance of reality. Let's use a simple analogy. Imagine a library that contains every possible book. Not just every book ever written, but every possible combination of letters. Most of the books would be pure gibberish, but somewhere in that library, you would find the complete works of Shakespeare. You would also find a version where Hamlet is a comedy, and another where Romeo and Juliet live happily ever after. The mathematical universe is like that library. Most of the mathematical structures it contains correspond to gibberish universes, sterile, chaotic, or fleeting. But within that infinite collection, there are bound to be structures that are as rich, complex, and ordered as our own. We are living inside one of the good books. This vision of reality is, of course, almost impossible to test. How could we ever prove that other, disconnected mathematical structures exist? Its main appeal is its philosophical elegance and its potential to be a final, all-encompassing theory. It suggests a reality that is far grander and more abstract than we ever conceived. It redefines what it means for something to exist. Under this hypothesis, existence is not about being made of atoms or energy, but about being mathematically consistent. If this idea is true, then our physical world is just a shadow, a tangible manifestation of a deeper, purer, and timeless mathematical reality. It's a humbling thought that the warmth of the sun, the coolness of a breeze, the feeling of love, and the curiosity that drives us to ask these questions could all, at their deepest level, be emergent properties of a set of equations. The universe, in this view, is not a story written in math. It is the math. And we are the part of the equation that has learned to read itself. The infinite universe and cosmic doppelgangers. Perhaps we don't need to invoke quantum branching, bubble collisions, or vibrating strings to find a parallel universe. Perhaps the simplest and most straightforward path to a multiverse is just to keep going in a straight line. This brings us to what cosmologist Max Tegmark calls the Level 1 multiverse. It's the least exotic of all the multiverse theories, as it requires no new physics and relies on just two simple assumptions: that space is infinite, or at least incredibly vast, and that matter is distributed more or less randomly throughout it. Let's begin with the first assumption. Is space infinite? We don't know for sure, but our best measurements suggest it might be. Observations of the cosmic microwave background indicate that the universe is geometrically flat on the largest scales. According to Einstein's theory of general relativity, a flat universe is most naturally an infinite one. It doesn't curve back around like a sphere. It just goes on forever. Of course, our universe could be finite, but just so enormous that the part we can see, our observable universe, looks flat, just as a small patch of the Earth's surface looks flat to us. But for now, let's follow the evidence and assume that space is truly infinite. Now for the second assumption, the distribution of matter. On the grandest scales, galaxies and clusters of galaxies seem to be spread throughout the cosmos in a roughly uniform way. There's no special center and no edge. It's a vast cosmic web of structure that looks pretty much the same everywhere. So we have an infinite space filled with a finite number of types of particles, quarks, electrons, etc., that are arranged in a roughly uniform pattern. This simple setup leads to a staggering conclusion. Things must repeat. To understand why, let's think about our own observable universe. This is the spherical region of space from which light has had time to reach us since the Big Bang. It's about 93 billion light-years in diameter. This region, our Hubble volume, is vast, but it is finite. And within this finite volume, there is a finite number of particles. While the number of ways these particles can be arranged is astronomically large, it is not infinite. Quantum mechanics tells us that there's a limit to the number of distinct states a particle can be in within a given volume. If you calculate the total number of possible ways all the particles in our Hubble volume could be arranged, you get a colossal but finite number. Let's call this number n. Now, if space is infinite, then there are an infinite number of these Hubble volumes out there, stretching far beyond our cosmic horizon. Imagine space as an infinite chessboard, and each square is a Hubble volume. You have an infinite number of squares, but only a finite number of ways to arrange the pieces on a square. By simple logic, the arrangements must eventually start repeating. In fact, in an infinite universe, every single possible arrangement must occur, and not just once, but an infinite number of times. This means that somewhere out there, far, far beyond our cosmic horizon, there is another Hubble volume that is arranged exactly like ours. Another region of space containing a galaxy identical to the Milky Way, with a star identical to our Sun, and a planet identical to Earth. On that planet, there is a person who is atom for atom identical to you, living out a life that is, up to this very moment, exactly the same as yours. This is your cosmic doppelganger. And not just one. In an infinite universe, there must be an infinite number of them. There are also regions that are almost identical to ours, but with one tiny difference. A universe where you wore a different shirt today. A universe where you never got that haircut. A universe where that one embarrassing thing you said in high school never happened. Every possible variation of our observable universe exists somewhere out there in the infinite cosmic quilt. This is the Level 1 multiverse. It's not a separate dimension or a quantum branch. It's just a distant region of our own universe, a place so far away that we can never see it or interact with it, because the light from it will never have time to reach us. It's the most conservative kind of parallel universe. It's a prediction of standard cosmology and statistics. How far away would your nearest identical twin be? The calculations are mind-boggling, based on the number of possible quantum states in our Hubble volume. A rough estimate places your nearest identical copy at a distance of 10 to the power of 10 to the power of 28 meters away. This is a number so large that it's meaningless to even try to write it out. It's a distance so vast that you could travel at the speed of light for longer than the current age of the universe, and you would not have even begun to scratch the surface of the journey. You will never meet your cosmic doppelganger. This idea provides a different kind of comfort. Unlike the many worlds interpretation, where you are constantly splitting into different versions of yourself, here you remain one, unique individual within your own observable patch. Your other selves are not you in the same way. They are just independent, identical systems that formed by chance in a distant corner of an infinite space. There is no connection between you. Their choices are not your choices. They are simply a statistical echo, a consequence of infinity's relentless logic. This vision of the multiverse doesn't require any exotic new physics. It just requires us to take the idea of infinity seriously. If space truly does go on forever, then the existence of parallel worlds isn't a possibility, it's an inevitability. It's a quiet, humbling thought that our entire world, with all its history, its art, its joys and its sorrows, might just be one pattern among an infinite number of others, repeated over and over again in the silent, unending tapestry of space. Cyclic universes. The Phoenix multiverse. So far, the multiverses we've explored have been parallel in space. There are other regions, other branches, or other bubbles that exist at the same time as our own universe, coexisting in some grand, timeless cosmic structure. But there is another way to imagine a multiverse, one that unfolds not in space, but in time. This is the idea of a cyclic universe, a cosmos that goes through infinite cycles of birth, life, death, and rebirth. In this picture, the other universes are not our neighbors, they are our ancestors and our descendants. The idea of a cyclic cosmos is ancient, appearing in various forms in philosophy and religion for thousands of years, but it has also been given serious consideration by modern cosmologists who have developed several modern models for how such a cycle might work. One of the earliest modern versions was the idea of the Big Crunch. Scientists once thought that if there was enough matter in the universe, the force of gravity would eventually overcome the expansion that started with the Big Bang. The expansion would slow down, stop, and then reverse. Galaxies would stop rushing away from each other and start rushing back together, faster and faster, until the entire universe collapsed back into an infinitely hot, dense singularity, a Big Crunch, the mirror image of the Big Bang. And from that crunch, some speculated a new Big Bang could erupt, creating a new universe in a process called the Big Bounce. The universe would be like a cosmic accordion, expanding and contracting in an endless cycle. This simple Big Bounce model has fallen out of favor, largely because of the discovery of dark energy. We now know that the expansion of the universe is not slowing down, it's accelerating. This seems to point towards a future of endless expansion, a big freeze, rather than a big crunch. However, the idea of a cyclic universe is not dead. It has been reborn in more sophisticated forms, often incorporating ideas from string theory and M-theory. One such model is the ekpyrotic universe, a name derived from the ancient Greek word for conflagration or fire. This model arises from the brane multiverse idea we discussed earlier. Imagine our universe is a three-brane floating in a higher dimensional space. In this model, there is another brane floating parallel to ours. These two branes are not static. They are drawn towards each other by a force. According to this theory, the branes move together, slowly at first, and then accelerate, eventually colliding with each other. This collision is not a destructive crash in the normal sense. Instead, the massive amount of kinetic energy from the collision is converted into the hot soup of particles and radiation that we identify as the Big Bang. The collision is the Big Bang. After the collision, the branes bounce off each other and begin to move apart again. As they separate, our universe, our brane, expands, cools, and evolves, forming galaxies, stars, and planets, just as we observe. But the cycle doesn't end there. After billions of years of expansion, the force between the branes eventually pull them back together again, leading to another collision, another Big Bang, and the start of a new universe. In this cyclic model, time is infinite. There was no first beginning. The Big Bang was not the creation of everything from nothing, but simply a transitional phase in an eternal cycle. Our universe is just one epoch in an endless series of epochs. The parallel universes are the ones that came before us and the ones that will come after us. This is a phoenix multiverse, where the universe dies in fire and is reborn from its own ashes over and over again. This model elegantly solves the beginning of time problem that plagues the standard Big Bang theory. It also offers potential explanations for other cosmological puzzles, like the nature of dark energy and the flatness of the universe. Proponents of this model believe it may even be testable. The specific process of the brane collision would produce a unique pattern of gravitational waves, ripples in space-time, that could be different from the pattern predicted by the standard inflationary model. If we could one day build gravitational wave detectors sensitive enough to detect these primordial ripples, we might be able to distinguish between an inflationary origin and a cyclic origin for our current cosmic age. We could, in theory, see the echo of the moment that birthed our current cosmic age.
There is something deeply peaceful and poetic about the idea of a cyclic universe. It replaces the linear story of a single birth and an eventual heat death with an eternal rhythmic dance. It connects us to a past that stretches back through countless previous universes and a future that will give rise to countless more. It suggests that the cosmos is not a one-time performance, but an endless rehearsal, constantly refining and recreating itself. In this view, the universe has no beginning and no end. It simply is, was, and always will be a timeless, pulsing heart of creation and recreation. We are just a brief conscious flicker in one of its infinite heartbeats. Philosophical puzzles, identity, free will, and meaning. We have wandered through the furthest reaches of scientific speculation, exploring realities that branch, bubble, repeat, and cycle. These ideas are born from mathematics and physics, but they don't stay there. They spill over, creating deep and fascinating ripples in the quiet pools of philosophy. The multiverse, if it is real, forces us to reconsider some of our most fundamental concepts, what it means to be me, whether we truly have free will, and how we find meaning in a cosmos of infinite possibilities. Let's gently explore some of these puzzles. First, there is the question of identity. In the quantum multiverse of the many worlds interpretation, a version of you is created with every quantum choice. In the infinite spatial multiverse, an identical copy of you exists in a distant galaxy. So who are you? Are you the sum total of all your possible selves? If another version of you in another branch makes a terrible mistake, are you in some way responsible? The gentle consensus among philosophers and physicists who ponder this is that you are the person confined to your specific branch or your specific Hubble volume. Your consciousness, your memories, your experiences create a unique continuous thread that defines your identity. The other versions of you are no longer connected to you. They share a past, but they have their own present and their own future. You are not responsible for their actions, just as you are not responsible for the actions of an identical twin you never knew existed. And yet, the idea can be humbling. It suggests that your sense of self, your unique identity, is defined not just by what you are, but by the specific sliver of a much larger reality that you happen to inhabit. Next, consider the thorny problem of free will. We have the powerful subjective experience of making choices. You chose to listen to this video. You might choose to have a glass of water soon. But if the many worlds interpretation is correct, every choice you make is realized. As you decide to have water, the universe splits. In one branch, you get the water. In another, you don't. All possibilities are played out. So did you really choose? Or did you simply experience the unfolding of one particular branch? This can feel like it undermines the significance of our decisions. If every path is taken, what is the value of choosing one? Some thinkers argue that free will is preserved. Your experience is that of making a choice and living with its consequences within your branch. The fact that other branches exist doesn't negate the reality and importance of your own journey. Your choices still shape your world, the only world you will ever know. Perhaps the multiverse just reframes free will, not as selecting one possibility from many, but as creating the reality in which your selection becomes true. Finally, we arrive at the profound question of meaning. If our universe is just one bubble among countless others, or one random pattern in an infinite space, does that make our existence, our lives, and our struggles insignificant? If there are infinite copies of you, does that devalue your uniqueness? It's easy to feel a sense of cosmic vertigo, a feeling of being lost in a reality so vast that nothing we do could possibly matter. But we can also choose to look at it from another perspective. Perhaps the multiverse enhances meaning. The fine-tuning of our universe for life is one of the deepest mysteries in science. The anthrotic explanation that we live in one of the rare universes where life is possible can feel like a lucky, meaningless accident. But in the context of a multiverse, it can be seen differently. It suggests that the cosmos as a whole is incredibly fertile, constantly experimenting with different laws and conditions, and in its infinite creativity, it is bound to produce universes like ours where meaning, consciousness, and wonder can emerge. Our existence might not be a fluke, but an inevitability of a creative cosmos. The meaning of our lives, then, is not given to us by some preordained cosmic purpose. It is something we create ourselves, here in our own rare and beautiful corner of reality. The fact that our universe is hospitable for life is an extraordinary gift, regardless of how many other sterile universes there are. Perhaps our purpose is to be the universe's way of knowing itself, of appreciating its own beauty. We are the conscious part of one of these cosmic bubbles, and our role is to observe, to understand, to create, and to care for the precious, fragile world we have been given. The existence of other worlds doesn't have to diminish ours. It can make us appreciate it all the more. It's like walking through a vast desert and finding a single, beautiful, thriving oasis. The barrenness of the surrounding sands doesn't make the oasis less wonderful. It makes it more so. These are not questions with easy answers. The multiverse is a mirror, and in it, our philosophical assumptions are reflected back to us. It challenges us to think more deeply about who we are and what we value. Whether the multiverse is real or not, the act of contemplating it is a deeply human one. It is an expression of our endless curiosity and our search for our place in the grand scheme of things. It reminds us that the universe, in all its possible forms, is stranger and more wonderful than we can possibly imagine. The Critic's Corner: Why the Multiverse Might Be Wrong. In our gentle journey through these extraordinary ideas, it is important to maintain a sense of balance.
The concept of the multiverse is intoxicating, but it is not without its critics. Many brilliant scientists and philosophers remain deeply skeptical, and their reasons are worth listening to with care. Their arguments are not born of a lack of imagination, but from a deep commitment to the principles of science and a healthy dose of caution. The most powerful and frequently raised objection is the problem of falsifiability. As we touched upon earlier, a cornerstone of the scientific method, as famously articulated by the philosopher Karl Popper, is that a scientific theory must be falsifiable. This means there must be some conceivable observation or experiment that could prove the theory wrong. For example, Einstein's theory of general relativity predicted that starlight would bend around the sun by a specific amount. If astronomers had measured a different amount or no bending at all, the theory would have been falsified. The multiverse, in most of its forms, seems to fail this test. If other universes are, by definition, causally connected to our own, how could we ever make an observation that would disprove their existence? If you can't see them, touch them, or measure them in any way, the claim that they exist seems more like a statement of faith than a scientific hypothesis.
Another powerful critique comes from a principle known as Occam's razor. Named after the 14th century philosopher William of Ockham, this principle states that when faced with competing explanations for the same phenomenon, one should prefer the simpler one, the one that makes the fewest assumptions. The multiverse seems to be a spectacular violation of Occam's razor. To explain the one universe we see, it postulates the existence of an infinite or near infinite number of unseen universes. Critics argue this is wildly unparsimonious. Why invent a colossal, unobservable superstructure just to explain some puzzling features of our own world? Is it not simpler to assume that our universe is all there is, and that we just haven't yet figured out the deeper reasons for its specific properties? They argue that invoking the multiverse is like trying to explain a single, unusual lottery ticket by claiming that there are an infinite number of other lotteries being played in secret rooms. It's a possible explanation, but it's not a very simple one. Furthermore, some critics are wary of the reliance on the anthropic principle that often accompanies multiverse theories. The argument that our universe is fine-tuned for life because we could only exist in a universe that is fine-tuned for life can feel circular and unsatisfying. Critics argue that this isn't an explanation at all. It's a surrender. It's giving up on the search for a deeper, more fundamental physical reason for why the constants of nature have the values they do. Science progresses by explaining why things are the way they are, not by saying they are this way because if they were any other way, we wouldn't be here to observe them. They hope for a future theory, perhaps a completed version of string theory or something else entirely.
that will show that the laws and constants of our universe must have the values they do for reasons of mathematical consistency, with no need for an infinite lottery of other worlds. Finally, there's a more subtle criticism about the nature of infinity itself. Many of the multiverse models, especially the level 1 and level 4 types, rely heavily on the concept of a true physical infinity. But is infinity something that can actually exist in the physical world, or is it just a useful concept in mathematics? Some physicists and philosophers argue that actual infinities lead to paradoxes and should be treated with suspicion. For example, in an infinite universe, anything that can happen will happen an infinite number of times. This leads to all sorts of strange conclusions, like the existence of Boltzmann brains, random fluctuations of particles in the void that momentarily assemble into a conscious brain before dissolving again. Some theories predict that in an infinite universe, Boltzmann brains should be vastly more common than regular, evolved beings like us, which calls the whole framework into question. These critiques are serious and important. They keep the conversation about the multiverse grounded and honest. They remind us that even the most beautiful and compelling ideas must be held up to the light of scrutiny. The debate between proponents and critics is not a hostile one. It is the healthy, essential process of science at work, pushing at the boundaries of knowledge and struggling to distinguish between what is real, what is possible, and what is simply a beautiful story. Living in a maybe, embracing the uncertainty. We have journeyed far. We have seen reality branch into countless streams, imagined universes bubbling up in a cosmic foam, and floated on membranes through hidden dimensions. We have contemplated infinite copies of ourselves in a boundless space, and witnessed the cosmos die and be reborn in an eternal cycle. We have also listened to the quiet, cautious voices of skepticism, reminding us that these grand visions are still unproven. So where does that leave us, here in the quiet of the night, suspended between these staggering possibilities? It leaves us in a state of maybe. And perhaps that is the most beautiful and honest place to be. Living with the uncertainty of the multiverse is not a cause for anxiety. It is an invitation to wonder. It is an opportunity to hold our ideas about reality a little more lightly, to recognize that the universe might be far stranger, larger, and creative than our everyday experience suggests. The multiverse is for now less of a confirmed fact and more of a powerful thought experiment. It's a tool for stretching our minds. For most of human history, our conception of the cosmos has been a series of expanding circles. First, the Earth was the center of everything. Then we realized it was a planet orbiting the Sun. Then the Sun became just one star among billions in the Milky Way galaxy. Then our galaxy was just one among trillions in the observable universe. The multiverse hypothesis is simply the next logical step in this great humbling. It asks, what if even our entire universe is not the final stage, but just one small part of a far grander reality? Embracing this uncertainty allows us to appreciate the history of science. Ideas that were once considered absurd speculation have, time and again, become accepted fact. The thought of a round Earth, of continents drifting across the ocean, of time itself being relative, all of these were once radical, boundary-pushing concepts. This doesn't mean the multiverse is destined to be proven true, but it does mean we should be cautious about dismissing ideas just because they seem strange or untestable with our current technology. Science is a long and patient game. The questions we ask today might not be answered for generations, if ever. But the act of asking them is what drives us forward. So how do we live in this maybe? We do it by focusing on the beauty of the question itself. The possibility of other universes doesn't change the reality of this one. The sun will still rise tomorrow in our sky. Gravity will still hold us to this earth. The laws of physics that govern our lives will remain the same. But our inner landscape can be different. Knowing that we might be part of an infinite cosmic tapestry can instill a sense of profound humility and connection. It can make our own problems feel a little smaller and the world around us feel a little more magical. It's a reminder that reality is not a solved puzzle, but an unfolding mystery. Think of it like standing on the shore of a vast, foggy ocean at dawn. You can see the waves lapping at your feet. You can see a few 100 meters out, but beyond that, the world dissolves into mist. You don't know what lies beyond the fog. It could be more ocean, stretching on forever. It could be a series of islands. It could be a completely different kind of world. You don't know. And in that not knowing, there is a kind of peace. You don't need to have the entire map to appreciate the beauty of the shore you're standing on. You can simply be present with the mystery. Listen to the sound of the waves and
Feel the coolness of the mist on your face. The multiverse is that fog, and we are standing on the shore, gazing out and wondering. We may never see what lies beyond, but the act of wondering, of imagining, of exploring the possibilities in our minds, that is a deeply meaningful act in itself. It is the essence of being a curious, conscious being in a universe that is still, and may always be, full of secrets. Conclusion. We began our journey tonight with a simple, almost childlike question. What if our universe isn't the only one? we have followed that question down some of the strangest and most beautiful paths in modern science. We've seen how the fuzzy uncertainty of the quantum world might imply that reality is constantly branching into a tree of parallel timelines. We've learned how the explosive birth of our cosmos might suggest we live in just one bubble in an infinite frothing sea of other worlds, each with its own unique laws of physics. We've explored the elegant possibility of our universe as a membrane, a single page in a vast cosmic book with hidden dimensions. We've even considered the idea that reality itself is a mathematical structure, and that our universe is just one of an infinite number of possible equations brought to life. We have seen that a parallel universe can mean many different things. It could be another world identical to ours, unimaginably far away in an infinite space. It could be the universe that came before ours in a timeless cosmic cycle of death and rebirth. Or it could be a timeline where you made a different choice this morning, existing just out of reach, forever separate yet forever connected. Each of these ideas is a different answer to the same fundamental question. And for each idea, we have listened to the quiet counterpoint of skepticism, the essential voice that reminds us to distinguish what we know from what we can only imagine. There is, as of yet, no proof, no photograph of another bubble, no message from another branch. The multiverse lives in the equations of our most advanced theories, a ghost in the mathematical machine. It might be the next great revolution in our understanding of the cosmos, or it might be a beautiful illusion, a grand story we tell ourselves at the edge of what we can know. We do not have the final answer, and that is perfectly okay. The value of the multiverse hypothesis for now is not in its certainty, but in its power to expand our sense of wonder. It challenges the very definition of the word universe. It forces us to confront the limits of our perception and the possibility that reality is infinitely more complex and vast than we ever dreamed. It is the ultimate expression of the scientific impulse to ask, what if? Where does this leave us? It leaves us here, on our small planet, orbiting our quiet star in our magnificent galaxy, inside our one precious and very real universe. Whatever other worlds may or may not exist, this is our home. This is the reality we are gifted with. The possibility of other universes doesn't make this one any less miraculous. If anything, it highlights just how special it is. In the vast landscape of all possibilities, this particular combination of laws and constants came together to allow for stars, for planets, for consciousness, for you. So as you drift off to sleep, let your mind be at peace with the grand mystery. You don't need to choose a theory. You don't need to solve the puzzle. You can simply float in the possibility. Imagine the branching rivers of time, the silent bubbles in the cosmic foam, the infinite worlds scattered across an endless night, and know that in this one, you are here. A flicker of awareness in a cosmos that is perhaps just one note in an infinite symphony, and that is more than enough. In the introduction, I asked you where you were listening from. I hope that now you feel you are listening from a place of quiet wonder, a citizen of a universe so strange and beautiful that it can dream up ideas as vast as itself. Whether you're in one world or one of many, may your rest be peaceful and your dreams be full of gentle cosmic light.